Welcome to 6034 Fall 2020 edition. Glad to have you back. Today we'll be talking about today's the second installment of the BaseNet saga, Recitation 6. I'll be recapping more or less what we talked about last time in Recitation 5, but it'll be a very lightning review. I encourage you, if something seems strange or you don't understand some of the concepts that I'll mention in the very beginning of Recitation, I encourage you to go to Recitation 5, watch that, and then come back to Recitation 6. Afterward, we'll talk about BaseNets more in depth. We'll go a little bit over, again, what we discussed previously a bit quickly, and then I'll add more of the applications of BaseNets in the context of 6034 and in the context of Bayesian inference. Okay. So here's the agenda. Again, probability recap is going to be very, very quick. And then the first two items of BaseNets are also, or not the first two, the first item, this deseparation, is going to be the same example that we did in Recitation 5. Okay. So as a quick reminder, the types of probabilities that we're working with here are joint, marginal, and conditional probability. A joint probability is one where, in the case where my universe is ABC, I am taking the probability of a well-defined event, as in all the variables in my universe have acquired a value, which we consider, when a variable acquires a value, is an event. So this is an event where all the variables in the universe have value. Then marginal is the probability of an event that is not completely defined within the context of the universe. I'm only interested here in this case in the events where a equals lowercase a, and there are cases where the other two variables b and c can take on other values, but I don't particularly care, so I sum over them and then I get the ratio of the number of events in which a equals lowercase a over all the events in general. So that's the marginal probability. Conditional is where I change my universe. So I go from omega being my universe to the series of events where b equals b lowercase b and c equals lowercase c. So that's a new universe, and I'm interested in within those events where b equals lowercase b and c equals lowercase c, which of them have a equals lowercase a. So that's the conditional probability, and one way you get to it is by dividing the joint probability, the one where all the variables are defined, by the marginal probability of the event over which I am conditioning. Then the extension of the conditional probability was chain rule, in which I merely multiplied the marginal probability here by the conditional probability on the other side. So you can see I have the marginal probability here, and I have, not the marginal probability, my universe is now smaller, it's only a and b, so this is the joint probability that was in the numerator before, and now I have the conditional probability multiplied by the marginal probability. And I can split this up either way. So I can do a given b times probability of b, or I can do b given a times probability of a. They're both equivalent, and I use this equivalence to derive Bayes' equation by dividing by the marginal on one side. So here I have the conditional probability a equals a given b, and that is equal to b given a, probability of a divided by the probability of b, the marginal I use to divide on both sides. That's it for types of probabilities and equations. Now I want to recap independence. We have two types, marginal and conditional. Intuitively, in both cases, independence means the same thing. It means knowledge of one variable does not give me any information about another variable. So the value that turns out in one does not affect the probability of another, and vice versa. In terms of marginal probability, what that means, I abbreviated it this way, is the a is independent of b if and only if a given b is equal to the probability of a given b is equal to the probability of a, and this is a consequence where if I take the joint probability of A and B, then the probability of A given B. This I can use the chain rule, the probability of A given B times the probability of B, but because of independence, this is equal to the probability of A times the probability of B. And the same thing in conditional independence, my apologies, except that now it's knowledge of C. I have knowledge of C, and knowing C makes it such that A and B are no longer informative of each other. Or it's not necessarily no longer, but when I know C, A and B do not inform each other, regardless of whether they informed each other before I knew C. So conditional independence does not necessarily imply marginal, and marginal does not necessarily imply conditional independence. Okay, and here's a brief recap of the number of parameters that we discussed in Recitation 5. I'm not going to do the full table because I'm going to go through an example of the number of parameters in a Bayes net. But it's good to keep in mind the equation for the number of parameters in a probability table when I don't assume any independence between the variables and when I assume all the variables are independent. And that's going to come in handy later when we're working with the number of parameters in a Bayes net. Okay, and this was the gold star idea of the previous recitation. Today it's also a gold star idea. It's the Bayes net assumption. I want to make a note that in the previous video I referred to this as the naive Bayes assumption, and I want to highlight that that was a mistake on my part. I mistook the Bayes net assumption with the naive Bayes assumption. They are two different things. This is, and I strongly emphasize, the Bayes net assumption, where each variable in a Bayes net is conditionally independent of its non-descendants given its parents. If you don't know what that means, again, please refer to recitation number 5, where I work through an example of how to use that. And regarding the naive Bayes assumption, I will be talking about it later in this recitation. Okay, so here's a brief recap of D-separation. First, we draw an ancestral graph. We link the parents by drawing an edge between them. Disorient the graph by erasing or deleting all the arrows on all the edges. Then we delete the givens and all the edges that connect to them, and we read the answer off the graph. And just a brief recap, if the two variables of interest are connected by a path, doesn't matter how many variables are or aren't in between, as long as there's a path from A to B, then structurally they are dependent. And if there is no path, then they are structurally independent. In the case of structurally independent, we know that they are marginally independent as well. That will never change. However, if they are structurally dependent, as in not independent, there's a path between them, that there could be a case, or it is possible that they are marginally independent due to the math working out that way. But it's not a common case. So this is the example that I worked through in the previous recitation. I'm just going to flip through these boards relatively quickly as a recap of how it is done. So the first step is to draw the ancestral graph. There I've deleted and all the variables that are not an ancestor of any of the variables of interest. Then we link the parents. We link the parents. We make the graph undirected. Then we delete the givens and their edges. And we read. There is a path between A and B, which means A is not independent of B given D and F. Okay, so number of parameters. I've changed around the Bayes net. I will work through this example in particular, and hopefully once you've seen this example, you're able to work through the example through this example. Through the example we just showed. I'll show it again after working through the number of parameters on this particular Bayes net, which is a little bit simpler. Okay, so first, let's take a look at A and B. And if you are curious about why I would choose A and B first, I encourage you to try, as an exercise, D-separation for A and B when nothing is given. And if you do so, you should come to the conclusion that both A and B are both independent when no further information is provided. So, if I were to draw a probability table, for A and for B, I would only need in reality one parameter, assuming, and big asterisk, this is all the variables in this Bayes net are Boolean. They either take a true or false value. So this is P1, and by the principle of exhaustion, this is 1 minus P1, this is P2, and then 1 minus P2. So there's one parameter, and the rest I get through exhaustion. If you're unfamiliar with the term or the principle of exhaustion, again, please refer to recitation number 5. Otherwise, I'll proceed. Okay, so I've noted that A and B both have one parameter, and the reason that they only have one parameter is because they have no parents. So now I'm going to work with C. I'm interested in the value of C, the value of A, which has a direct connection to C, and the probability of C given A. Reminder that because of the Bayes net assumption, I could make this the probability of C given A, B, C, D, A, B, and D, and it would amount to the same thing. It would amount to the probability of C given A because of the Bayes net assumption. If you don't know exactly why, then I encourage you to try a few exercises where you write the joint probabilities and you reduce them using the Bayes net assumption and the chain rule. Okay, so this is true, true, false, false. It's a standard truth table. True, false, true, false. Okay, so when A is true, that is one universe, and that means I need one parameter. When A is false, I'm in a separate universe, given that A is false. So I'm going to need a separate parameter for that. But now, A is true again, C is false, but I'm back in the universe where A was true and I already have a parameter here. So I can probably get away with 1 minus P1 by exhaustion, and the following entry, A is false, I already have a parameter, P2, describing the probability of C given A for that universe, so I can get away with 1 minus P2. So I have two parameters, and these I got through exhaustion. Exhaustion being that all the probabilities in a universe need to sum to 1.0. There, I said it. Okay. So I have a probability, this is in the way, probability, not a probability, two parameters here, one parameter. Let's work with D now. Oops. Have the probability of, actually, never mind. D, A, and B, its parents. And the probability of D given A and B. So I'll build a similar truth table to earlier. Don't worry if you can't see it. Okay, so I want to make a similar analysis to what we did for probability of C given A. I'm conditioning on two variables that each can take two values. So first, let's look at the first one. I have a universe where A is true and B is true. I have a universe where A is true, B is false. A universe where A is false, B is true, and a universe where both of them are false. So I have four distinct universes. And they keep repeating themselves. For each universe, I'm going to need at least one parameter. So I'm just going to start here. P1, P2, P3, P4. And now I'm back in the same universe. As in the universe for which I defined P1. And the only thing that's different is that D, instead of being true, it's false now. And that's all the probabilities in the universe. So I know that this one can be summarized as 1 minus P1. The following one can be 1 minus P2, 1 minus P3, and 1 minus P4. So I have a total of 4 parameters. And the rest I get through exhaustion. Okay? And exactly the same argument can be made for E. I won't bother writing the whole probability table because it's exactly the same as the probability table in the previous slide, except that I changed the header to ECD, E given C and D. So note that the rest of this is missing, and this is, I just didn't bother to write the part that I would get for free from exhaustion. So I get P1, P2, P3, and P4. Same argument. So I get 4 parameters for E as well. This means that I have a total of pardon me, 12 parameters. But 12 parameters, and this is an important point to note, 12 parameters under the Bayes-Net assumption. And what I mean by that is 12 parameters where we assume that each variable is conditionally independent of its non-descendants given its parents. So let's see how that stacks up to the other two assumptions, or lack of assumptions. So the first one is the assumption that everything is independent. If you remember the formula, it was the sum of the range of each variable minus 1, and that was it. So I sum the range of all the variables in the universe, as in how many values it can take. I subtract 1, and that'll give me the number of parameters that I need. I have 5 variables, and they each can take 2 values because they're Boolean. And I subtract 1 every time I sum 2, which means I only need 5 parameters under the independence assumption. Okay. I noticed I had pulled up the wrong notes, so now I'm up to speed. Okay, assume now, or not assume. Let's now put the Bayes net assumption here. And that's solve parameters. And then the other, not assumption, but the lack of assumption was where you have assumed absolutely no independence between any of the variables. And how does that look? If we recall from the formula, it was a product of the ranges of all the variables minus 1. So what that amounts to, I have 5 variables and they have a range of 2. So it's 2 to the 5 because they're 5 variables minus 1, 31 parameters. And that's the shocking part, because yes, naive Bayes is not ideal, but it's almost 3 times less in terms of number of parameters as the no independence assumption. And to ground this a little bit, this is a very small toy example, but depending on how you are able to use a Bayes net to model a particular phenomenon of interest, you can have thousands, if not tens of thousands of parameters, and using the Bayes net assumption can bring the complexity down of that modeling, or at least of storing those probability tables, down considerably lower than if you were to use no independence assumptions and you were forced to store all the probability tables one by one for all the events. An example of how those computations can be simplified a lot. Let's apply the Bayes net assumption one more time. Okay, I'll make a notational note. If I write A, it means that A is true. If I write not A, it means, as in A with that little bar, A is false. And let's say you're working on a problem where you need to figure out the probability of the following event. Calculating the joint probability of between 5 variables is a very complicated and intensive calculation, particularly depending on what the variables mean and the context, of course, but it's no small feat to calculate that monster joint probability, depending on the information that you have available. But what if we could simplify it, even if just a little bit, using the Bayes net assumption? So I'm going to use the chain rule, which is not an assumption, it just is a rule that I can apply in probability regardless of the assumptions. So I'm going to use it on E. So I want the probability of E conditioned on everything else. Conditioned on D, not C, B and A, times the probability of D given not C, B and A, times, I'm going to write it below because I'm running out of space, the probability of C given B and A, times the probability of B given A, finally the probability of A. So now let's apply the Bayes net assumption. If we apply the Bayes net assumption, the first thing to note is when I introduced the first set of parameter calculations, A and B, I said if you perform D separation with nothing given, then you'll see that A and B are structurally independent. So that's the first thing that I'm going to do. Because they are structurally independent, the probability of B given A is the same as the probability of B. So I can rewrite that. Further, not C has as a parent A, and it's also given. I'm looking for the probability of not C given B and A. And because of the Bayes net assumption, it's independent of its non-descendants, or conditionally independent of its non-descendants. So I can eliminate B from that computation. The same for D. The parents of D are A and B. C is a non-descendant. I can eliminate it thanks to B and A being given. And then for E, I can eliminate B and A because they are non-descendants and its direct parents are C and D, in fact. And this is the final form that the above equation takes. And you can see this is much simpler to calculate than the probability of the joint probability of A, B, not C, D, and not E. Did I miss a not E? Oh, I dropped it. Apologies. So there's not E, not E. Yeah, now it's correct. So this is much simpler. Right, so this is an example of how the Bayes net assumption can simplify computations, and there are actually more examples where this is the case. But first, before leaving the topic of number of parameters, as I alluded to earlier, I encourage you to calculate the number of parameters in this particular Bayes net and use it as a test to make sure you understand when variables are dependent or independent, structurally speaking, and how to build these probability tables that will allow you to determine the number of parameters for each variable. So now, as promised earlier, we're going to talk about the naive Bayes assumption. And the naive Bayes assumption says that the features of a data point X, so feature x1, x2, x3, so on and so forth until xn, are conditionally independent of each other given the final classification y. And I encourage you to test this out on your own by performing d-separation between x1 and x2, or between x2, x3, or all the variables at the same time given y. And you'll see that it is a manifestation of the Bayes-net assumption. Hence, some of the confusion about, Bayes-net assumption versus naive Bayes assumption. But the naive Bayes assumption formally is that the features themselves of a data point are independent when a class is given, when its classification is given, and I'll proceed to an example because that'll show why we call it naive Bayes. So let's consider the example where we're tasked with classifying people. So we have a person, and we know there are two features: whether that person likes toys and whether the person likes vegetables. So let's say that a person likes toys or likes vegetables but does not like the other one. So if you like toys, you don't like vegetables, and if you like vegetables, you don't like toys. If you like toys but don't like vegetables, those two features are dependent on each other. Knowing that a person likes toys, the way it is set up now, gives you some knowledge about whether the person does not like vegetables. But let's say I tell you the answer, that this is a child. The naive Bayes assumption says that given that the person is a child, whether the child likes toys is independent now of whether the child likes vegetables. And that's why it's naive as well. There is some dependence between the two features when the class is known, but we assume that they are independent. So we say for the other one that it's an adult, and if you like both, then that's probably me. So a bit more formally, if you know whether a point is an adult or a child, the features, I'm just going to abbreviate it to toys or vegetables, are independent. If you don't know, and by this I mean if you don't know whether the person is a child or an adult, then the features are dependent. Okay. And now for in this case, it's a very toy example. And do we like toys here in 6034? At least toy problems and toy examples. No, what I mean is it becomes a little bit too simple because you're already given the classification and you know the two features. The majority of the cases, it's not exactly that way. The majority of the cases, you know the features and you're trying to find out what class is this? What classification do I give this? What is the most likely classification for this? And that's where this inference comes in, the Bayesian inference. And you'll see also the power in the next slide or two, the power of the naive Bayes assumption in simplifying calculations. So let's say I have a variable x or a point x whose classification I don't know, but I know the features. x1 is A, x2 is B, and x3 is C. So I know its features, I just don't know its classification. And its classification is, so y is the final classification, and it can be any number, it can be anything. And the final classification I'll represent as lowercase y. So I want to figure out what y, this lowercase y is. And to put it more formally in mathematical terms, the goal then is to find a y, or the value of y in the range of the uppercase y, such that I maximize the following probability. I forgot a parenthesis there. Don't be scared by the argmax. What that means is the argmax will give me the lowercase y value that causes this probability value to be the greatest out of all the other the lowercase y values. So in reality, what is happening is I am maximizing this using or given this evidence. In a little bit more context, this y given this possible classification given the evidence we refer to as the posterior probability. I typically remember it using the mnemonic posterior probability is post-evidence, posterior. That's just my trick, not necessarily the best, but it works for me. So this is the probability. After taking evidence into account. So let me write it out a little bit more. I'm going to borrow this. Oh, that's a lot. There. I don't need the x anymore, just to give me a little bit more space. So this is my goal. I have the posterior probability there, but Bayes' rule already gives me a very powerful equation or equality to write this. So I can rewrite this as I still have the argmax. I'm still looking for the y that maximizes the value, but now I have the following. now it's the probability of x1 equal to A, x2 equal to B, x3 equal to C, given the classification. So what is the probability of this evidence occurring, or of me seeing the evidence, given that this is the classification that I have? Times the probability of the classification even happening in the first place, and then divided by the probability of x1 equal to A, x2 equal to B, x3 equal to C. So the probability of seeing the evidence in the first place. Give me 1 second. Yep. Let me close the bracket. Okay. So now I want to make the following observation. This denominator. That is generally fairly hard to compute. It's seldom the case where people seldom compute the probability of the evidence. And it's for a reason too. It's hard, and it's not actually necessary. Notice that in the argmax, I'm changing the y. Which possible classification am I working with? And that's going to change the numerator here. What is the probability of this evidence given a particular classification, and what is the probability of that classification? But the denominator itself is never going to change. At least not in this argmax. Which means if I want to find the value of y that maximizes this entire equation, or this entire fraction, in reality, I'm only trying to maximize the numerator, because the denominator is never going to change. So I'll write it here. So when y, lowercase y changes, that's an ugly y. So when lowercase y changes, only the numerator changes. So I'm going to rewrite this as tilde argmax. I'm still trying to find the argument y that maximizes the equation, but now I'm just trying to maximize the numerator. Okay? And now, so this is already looking a lot simpler. I don't have to calculate the probability of the evidence. But now I want to make it even simpler using the naive Bayes assumption. And what it says is the features are independent of each other given the classification, right? So I can simplify this even further to be individual probabilities almost. The probability of x1 equal to A given y equals y. The probability of x2 equaling B given y equal to y. Probability of x3 equaling C given y equal to y. And then finally the probability of y equaling y. Okay, and one final note. So this is much simpler. Emphasis on all the much, because we've gone from the original y equaling y given all the evidence to the probability of each individual feature happening given that that y is equal to lowercase y. To put it in simpler terms, remember the example about the adult versus the child. Given a child, what is the probability that a person would not like vegetables? That's what we're asking, instead of asking in the previous equation, for example, what is the probability that a person does not like vegetables and likes toys, given that the person is a child? So the first question, the one about only being, the one where I only asked about toys, is obviously much simpler to answer and much more straightforward from a probability point of view, because you're only taking one variable into account. And this is yet another case of how this reduction of parameters and how this naive Bayes assumption and the Bayes net assumption are so powerful in simplifying these assumptions and allowing us to make good approximations, sometimes good approximations, when they are properly built, when you properly build a Bayes net and you properly outline the features. Okay, so now we're going into the last part of this recitation, the model selection using Bayes nets. So we start with several possible models. MI that could explain the data or the evidence. And when I say the data or the evidence, I mean you have some data or some observation that you made, and you want to find the likely cause or the likely explanation that would say, okay, that makes sense. Just to give an example. Then, once you have a set of models, you pick the model MI that maximizes the probability of MI given the data. And of course, this is equal to the probability of the data given the model, the probability of the model itself, and the probability of the data. And as a note, remember that this is the posterior probability. This is the prior probability. The probability of the model or the hypothesis happening in the first place. And this needs to be known to you in order to carry out these computations. Then you also need the probability of the data, but we've already established that because we're trying to maximize the numerator, because the denominator does not change, the data does not change in these examples, then in reality we're trying to maximize the probability of the data given the model times the probability of the model without concern for the denominator. And that is because, to reiterate it one more time, the denominator does not change across MI. And so let's work through an example. This is from the 2010 6034 final exam. I have the following setup. You have two coins. One is a fair coin. Whenever you flip it, you get either heads or tails with a probability of 0.5 established here, and you have a bias coin that has two heads. So the probability of heads coming up in a toss is 1.0, 100% probability. And you have two models to explain what could be happening, one observation that you've made. Suppose that your friend is the one that has the 2 coins, and he tells you or she tells you a series of flips. That would be the data here. Yeah, your friend tells you, I got heads, tails. And you want to choose a model that explains best, or that makes it more likely that that was what was supposed to happen. And you have model 1, which says your friend drew a coin out of wherever your friend keeps coins, and tossed it, put it back, then drew it again, tossed it, put it back, drew another coin, tossed it, put it back. So each time a coin is drawn, flipped, and put back. And the second model says your friend only took out a coin and flipped it 3 times, then put it back. Those are 2 models that you can use to explain heads, tails, and you want to figure out which model best suits the data. Which model, given the data, is most likely what happened. So you want, argmax again. So it's either you want the model that produces the largest value in here. The model that maximizes, that is the most likely given heads, tails. So let's start with model 1. I've already written the equation, the base equation, and I'm going to start by applying the naive Bayes assumption. Notice that one thing to keep in mind is, and this is one way to think about what is going on. So my friend drew a coin and used that coin to make a toss. Coin 1, toss 1. Then drew another coin, made another toss, then drew a third coin, and made another toss. So looking at this, what is happening? So when I frame it this way, it doesn't seem as though there's any direct connection between the tosses themselves. So I'm inclined to apply the Bayesian assumption, and in the following way. Not the Bayesian assumption, the naive Bayes assumption. So the probability of getting heads given first model times the probability of heads given the first model, the probability of tails given the first model, times the probability of the first model divided by the probability of heads, tails happening in this thought experiment. So let's continue by simplifying this. I don't need this. Because the tosses and the coin flips happened next to each other, I separated the heads, tails into the probability of heads given model 1, the probability of heads given model 1, and the probability of tails given model 1. So these are separate, and I drew this little toy diagram because I love toys to show how you can think about this problem, or how you can think about this model setting up the problem. So I'm going to erase this briefly, and I'm going to proceed to calculate the probability of heads given model 1. So this is equal to, in model 1, I either draw a fair coin or a biased coin. So it's the probability of heads given a fair coin times the probability that I drew a fair coin. Or not me, my friend. That my friend drew a fair coin. Plus the probability of heads given that my friend drew a biased coin times the probability of drawing the biased coin. Both coins are equally likely when drawing from your pocket, so there's 50-50 chance of getting the biased coin or the fair coin. So that's just 1/2. If the coin is fair, you either get heads or tails, that's a 50% chance. And if the coin is biased, as we said earlier, it has 2 heads, so the probability of heads is 1. So this is equal to 1/2 times 1/2 plus 1/2 times 1.0. Just to make clear that both of those are 1/2. And that's equal to 0.75. Okay, and I need the probability of tails given M1. And I'll show you both an easy way and a needlessly complicated way of performing this calculating tails given M1 now that I know the probability of heads given M1. The easy way out is to look at your setup. In this universe, when I say M1, the model 1, where let's say M1 is the given. That's my new universe. A coin toss can either be heads or tails in that universe. So I already know that the probability of heads given M1 is 0.75. That means the probability of tails, by exhaustion principle, is just 1 minus the probability of heads given M1, which is equal to 0.25. The more complicated way of doing it is similar to how I did for the probability of heads given M1, just with tails. Tails given fair times the probability of the fair coin being drawn, times the probability of tails given biased, which is 0, times the probability of the biased coin. Okay, and you can carry out these computations to see that this is 0, and this is 1/4, so it's 1.25. So I'm just going to write that the above equation is proportional to 0.75, 0.75, 0.25, 0.5. And that's equal to 3/4 squared, 1/4, and 1/2. So we know the probability of M1 given the sequence H8 heads, tails. Now on to model 2. This model, and I'm going to draw an example of, I'm going to draw a toy Bayes-net in order to showcase what this model is doing. In this one, your friend drew a coin and flipped 3 times. Which means you can't really separate the the heads from the tails, the sequence of tosses anymore. Even though technically via deseparation you could say they are structurally independent, you can't because you don't know the coin that was drawn. You would be able to if you knew the coin, but in this case you don't. So you don't have you wouldn't be able to say if this is A, B, and C, this is the coin, you wouldn't be able to perform this deseparation because you're missing this information. Because you're missing this information and I can't separate heads, heads, and tails anymore, the following is what needs to happen. The above equation is equal to the probability of the sequence heads, heads, tails, given that a fair coin was drawn. This is why I made the toy drawing for the previous part as well, because if you were to conduct deseparation on the previous graph, you would get that the heads, and tails, those three tosses are independent of each other, structurally independent of each other, and you get the separation. But in this case, it doesn't work out that way because of the nature of the model. So I have to calculate the probability of this entire sequence given the coin. And now that the coin is given, then I can calculate separate, now that the coin is fair, I can calculate probability of heads, probability of tails individually. But before this step, I couldn't. Times the probability of fair plus the probability of the sequence heads, heads, tails given the biased coin was used times the probability of the biased coin, and then the probability of the model, the second model, divided by probability of HHT. I've established many times that this is not needed, and I'm only interested in the numerator. And I still want to bring your attention to, I really want to emphasize that you understand what is happening here. In the second model, notice that in the second model, I either drew the fair coin or the biased coin, and that's what caused the sequence heads, heads, tails. So I am summing, so this sum, this sum represents the universe M2. Okay. If we look at this in particular, if we have the biased coin, the probability of heads is 1.0, the probability of tails is 0. So given that I drew the biased coin, do I get the sequence heads, heads, tails? And that is a no. So automatically, this computation becomes 0. And my only interest then is the probability of heads, heads, tails, given that I drew the fair coin. I'll write proportional because I deleted the denominator. Okay. As I said earlier, now this is given, which means heads, heads, and tails are independent. but until I knew the coin, it wasn't independent, which is why I had to start by splitting up the M2 model into fair and biased. So the goal was to go from M2 to a point where I could leverage the structure of this model, or the Bayes net, where I basically split the M2 model into cases where I was able to use the Bayes net assumption to simplify the following calculation. Because now I can have probability of heads given fair, probability of heads given fair, probability of tails given fair, and the probability of M2. And what this simplifies to is, oh, I'm missing something. The probability of fair, the probability of having drawn the fair coin, and now the probability of M2. This is 1/2, this is 1/2, this is 1/2. We said that it's a 50-50 chance which coin was drawn, so this is 1/2, and M2 also 1/2. So this is equal to 1/2 to the 5th power. Now to summarize the results so far, this is 3/4 squared from earlier, 1/4, and then 1/2. And then this is 1/2 to the 5th power. Now the probability for the final punchline, M1 given HHT, heads and tails, is greater than the probability of M2 given HH tails. So if we stare at this, what this is saying, or the way I interpret this, is given that the sequence of tosses heads tails happened, it's more likely that the person who made the coin tosses chose randomly between the two coins, tossed it, put it back, and then chose randomly again. In other words, M1 explains the data better. M1 explains the data better, and you've just seen how in the following slide, if you take anything home, it's after this recitation is the Bayes net assumption and the naive Bayes assumption. A very quick recap, nothing special. The Bayes net assumption is that a variable is independent of its non-descendants given its parents. The naive Bayes assumption is that the features are independent of each other given the classification. In this recitation, you saw how these two assumptions are both related to each other, and how they have the power to simplify computations greatly, to a point that we can make these calculations by hand. You saw how the joint probability of 5 variables was simplified to a couple of conditional probabilities, and how the coins problem, when interpreted the right way with Bayes net assumption, and with Bayes net assumption mainly, that we were able to calculate the probability of model 1 given the data, model 2 given the data, and compare them and choose the most appropriate model. I want to end on making a cautionary note. In the slide before the examples, the model selection, I mentioned that you start with several possible models, MI, and you choose which model explains best the data. And that is a really big asterisk, because this is where the fundamental limitation of Bayes nets comes in. This is now starting to fall outside of the scope of 6034, but I think it's a very important piece of information that would allow you to take Bayes nets and further models based on Bayesian inference with a grain of salt. And that is, notice that we are choosing between a set of models. We're not creating models. So let's say, what if what the person was doing, the person who had the 2 coins and was choosing between them and tossing, let's say the person wasn't choosing between 2 coins but was choosing between 3 coins, one that's biased towards heads, one that's biased towards tails, and one that is actually fair. No matter how much evidence we would have gotten from heads, heads, tails, and then suddenly 10 tails and 1 heads, we would have never concluded using the Bayesian inference that person had a 3rd coin. And the reason for that is that we didn't have a model that said there are 3 coins. So the danger of Bayesian inference is, if you don't start with the correct hypothesis or set of hypotheses, you will never find the right answer. And that's the key weakness of Bayesian inference systems. It's that in the set of hypotheses or in the set of models that you're starting with, the correct one has to be in there, which to a certain extent defeats part of the purpose of solving the problem, because you can't, even though you arrive to the solution, you started out with the solution in the first place. And there are 2 ways in which people handle this. Typically, you either take absolutely all the possible universe, you go through the entire universe of models or hypotheses, and you make them, and you assign a probability greater than 0 to them. So you basically tell the model anything is possible. The person can have no coins, the person can have 1,000,000 coins in wherever, in your purse or your pockets. And so at one point, it becomes both intractable and impractical to perform such a calculation between so many different hypotheses. Notice it wasn't very much trouble because it was a toy example, but these problems can get very complicated, and if you have thousands of hypotheses, it becomes untractable. The second way in which people try to mitigate this problem is by making it hierarchical. You could have one layer of Bayesian inference that says the model is biased, the coin is biased, or the coin is fair. And then the second layer, if you go down the bias route, the coin is heads biased or tails biased. So that's one way. But then you run into the problem that maybe you don't need to put a positive probability in the lower layer, but now you've moved the problem one layer up. So you need to have the correct set of hypotheses in the top layer in order to arrive to the solution on the lower layer. So there's an inherent need for the correct hypothesis to be in the priors. With this discussion, I've gotten far out of the scope of 604, but I thought it pertinent to leave you with the final gold star idea, aside from Bayes net assumption and the naive Bayes assumption, that Bayes net will not be able to infer a new hypothesis that is given to it. So if the correct hypothesis is not at the start of the Bayesian inference will never find the correct answer. And with that piece of knowledge, I leave you to practice more Bayesian inference, to make the most of it, and to make it a a valuable tool, because it is a valuable tool in your tool set as you think about different inference and artificial intelligence problems. And I'll see you next time with another tool.